So you should be able to see me. I am simultaneously live now on TikTok and on YouTube. So YouTube is a trial. We're starting this out to try it out. So can you let me know if you can hear me okay? You should be able to write in the chat for both platforms. Yeah, so the reason that we're on YouTube as well is because I know that not everyone has TikTok. So this was supposed to be the last TikTok live of 2020 to celebrate all of the times that we've been able to see Atlas this year. And if it's your first time, then welcome. So I think on YouTube, if you can let me know if you can hear me okay. It is quite noisy in the cavern. Yeah, hi, thank you. Excellent. So welcome, we are live in the Atlas cavern. TikTok sound is good, thank you so much. So what I'm going to do is I'm going to show you the detector. I'm going to have to be really careful. I can't actually show you my setup, but it is quite homemade, let's say. So I have to make sure I hold it steady during this tour, otherwise you will fall, and we don't want that. So what I'm going to do is I'm going to show you the detector, and then maybe if we have 5 minutes, we might say hello to one of my Atlas colleagues who's here in the cavern too. She's about to give a tour to a school. So she's going to be sharing the excitement of the Atlas experiment and the cavern with a school, so some students. But maybe we get to talk to her before she goes and does that. So first of all, I'm going to turn these cameras around like this. So here you should now be able to see the Atlas detector. So where I am right now is I am 100 meters underground on the Swiss-French border, basically just outside of Geneva in Switzerland, but right next to the border of France. And this is the Atlas experiment. So this is one of the 4 main experiments on the Large Hadron Collider at CERN. And so we have a question on TikTok asking, do these tours also happen at CMS? So yes, there are tours at CMS. So the reason that I always do Atlas is because I work on the Atlas experiment. I am trained to come down here into the cavern and to show people around here both in person and online. I'm also a physicist, that's my day job on the Atlas experiment. But I have many amazing colleagues who also show CMS. So there are no aliens down here. Sorry to disappoint if that's what you were here for. Keep an eye out though. I mean, if you see one, let me know, but no, there are no aliens down here. So, okay, I think Zilka has to connect to the school, so maybe we'll see her later. Great, so what we can see now is actually the edge of the detector. And what I might do is I might head over this way first so that Zilka and I are not shouting over each other. So we're going to go for a little walk. Yeah, there's a crane. Let me show it to you quickly. I don't want to film people working too much because there are people up there. So we are currently shut down right now. Oh, welcome, somebody joining from Kenya. That is very cool. So we are not running. So the Large Hadron Collider is switched off. And so Finir said, do we shout, he's behind you if we see an alien? Yes, please. I would like as much notice as possible. I wish I could take a picture of the setup because it's quite cool being able to see this on both screens at once, except for the fact that both of my phones are currently being used for the setup. So we are now on the other side of the detector. So what you might, oh, that was a bit loud. What you might notice is that it's symmetrical. So we have the same view on this side as we had on the other side of the detector. And that's a very important point. It's for a reason. So let me go over to this diagram first. We have a nice diagram of the whole detector over here. And I can show you what the detector looks like if we zoom out. So this is the Atlas detector. So as I was saying before, it is one of, oh, let me tilt down so YouTube can see it properly. It's one of 4 main experiments on the Large Hadron Collider. And what happens is, so the Large Hadron Collider, this is a particle accelerator that accelerates protons to almost the speed of light. It's to 99.9999991% of the speed of light. Hold on, let me put do not disturb on. There we go. Otherwise we're going to get those notifications all day. So it's so very close to the speed of light, which essentially, when the protons are traveling that fast, because they're not massless particles, it means that the protons gain energy, they gain mass, and then when we collide them together in the center of our detectors, so one set of protons goes this way, one set of protons goes this way, and they collide together in the center of our detector. Oh, thank you for the nice comments. Hey, you hit your steps. Yeah, not quite, but by the end of the tour, I am pretty sure I will hit my steps by going up and down all these stairs. So, when the protons collide in the center of the detector, we use essentially Einstein's equation E equals mc squared, and this it allows us to transform particles from one type into another. And so these protons change into particles that exist elsewhere in our universe, but they don't last for very long, and so it's very difficult to measure them if they're not hanging around. So what we do is we create them in these collisions, and then, as I said, they don't last for very long, so what they do is they quickly transform into lighter particles, like electrons, or photons, or muons. These are much more stable particles. And these particles come off in all directions from the center of our collision. Yeah, E equals mc squared, very famous. So Einstein, there's a lot of the work by Einstein that really is the foundation, and many other fantastic scientists, the foundation of this work. Thank you so much for the rose. So these collisions happen, these particles are created, and they come off in all directions. So you can think of it's like the shape of a firework. So when the firework happens in the sky and those spray of colors happen in all directions, that's what's happening in the center of our detector. Although it's not colorful, we can't see it. And then what we do is we surround our detector with different types of detectors. Yeah, we surround the collision point with different types of detectors. And the job of these detectors are to measure the different particles. So what we have in the center of the detector is called the tracking detector, and the job of the tracking detector is to measure charged particles. So electrons and muons, these have an electric charge, and so they leave a trace in the detector as they travel through, and that way we can measure them, and we can measure this track as it's passing through. Then we have the calorimeters. So these green and orange sections of the detector are the calorimeters, and the best way to remember what the job of the calorimeter is it measures the energy of particles. And if you think of the word calories, so that measures the energy that you get from food, specifically to do with heat, then the calorimeters measure the energy, and how they do that is the particles deposit their energy in the detector. This is converted to an electrical signal, and then we measure it out of our detector. And then on the outside of our detector in blue, you can see surrounding the rest of the detector, we have the Muon spectrometer, and this is a section of our detector that is specifically, thank you for the baguette, and if that's related to the bird dropping a baguette in the power source, then that's brilliant. So if anyone on YouTube is wondering, on TikTok people can send gifts and little icons, and they're often different things. So somebody just sent a baguette, which I find funny. Yeah, so surrounding the detector we have the Muon spectrometer, and it's specifically designed just to measure muon particles. Let me try and hold this a bit steadier. And the reason is that muons are they're the heavier cousins of electrons, so they're almost identical to electrons, except for they are more massive. And this means that they interact differently, they behave differently in the detector, and they travel all the way to the very edge. So the blue circles, so there's a question on YouTube asking, the blue circles are the new wheels or the, let me bring that up again. Are the new wheels or the muon chambers? So they're all to do with the muon detector. These are the old ones. We say old, but these are the originals. They're large, and we'll look at those in a second. So I'm going to go back to the detector in a second. The new ones, you can't really see great. You can see it better on this side. The new ones are these ones here. So we removed these wheels, the previous versions, and they're called the small wheels because if you look at this size, this is 10 meters in the real detector, and this is 25 meters. So the large wheel. And so yeah, their job is to measure muons, and something that's really useful about muons is they leave quite a clean signature in our detector. It's quite easier, it's easier to identify muons than some of the other particles. And so we use them to what we call triggering. But what that means is it's data selection. And we say that if an event, if something that comes from one of the collisions in the center of our detector has a muon in it, it's probably something we want to look at. That's probably an interesting event, and we want to keep it. So we use muons are very important for data selection. Thank you very much for the feedback on YouTube. So I just saw somebody said that they were supposed to have a tour in January and it got cancelled. Yeah, I'm really sorry for you for that. It's very unfortunate. We have different restriction levels at CERN due to the pandemic, and because the rates have been rising, unfortunately all public tours had to be cancelled. And it's one of the reasons that I've been so keen, especially this year, to do as many online live tours as possible. I know it's not the same as coming here in person. I hope all of you get to come here in person and see the detector for yourself, because I think it's really special to be in the cavern and get a sense of the scale of the detector. But unfortunately, right now it's not possible. So now let's go back to look at the detector. So we were looking at that diagram, and that showed us the detector as a whole. And so now hopefully when you look at the detector here, you get a better sense of what you're seeing. And so what I didn't talk about when I was describing the detector is what is this massive silver thing here. So this is part of the toroid magnet system. So it's connected to, or it's the same system as these silver and orange sections of the detector there. And the reason that we have strong magnets in our detector, Andrea says you feel comfortable in virtual visits. Thank you so much. I'm really happy to hear that. So the magnets are very, very high strength magnets, and they bend the path of the charged particles. So I said, for example, with the tracking detector, that we measure the track of the charged particles. If we introduce a magnet into that, into our system, it bends the track. It curves it, essentially. And the curve tells us the charge of the magnet, and the curve tells us the charge of the charged particle, and how much it bends can help us to understand the momentum of the particle. It helps us with identification. So it can tell us whether it's an electron, which is very light, and so in the same strength magnetic field, an electron will bend much more than a muon will. And so that helps us with identification for the particles. And so somebody asked how strong. So this magnet system, the toroid magnet system, is 3.5 Tesla, which is very strong. And in the center of the detector, we have another magnet system called a solenoid magnet, and that's at 2 Tesla. So in Atlas we have 2 magnet systems. In CMS they just have the solenoids, and it's in their name, the compact muon solenoids. So it's not the same as a tokamak, which I think is related to the fusion studies, right? But I'm not an expert on those, so I couldn't say more than that. So this machine, this part of the detector, so somebody in TikTok is asking, is the machine located in France? So the machine, this detector is located in Switzerland, but the Large Hadron Collider is a 27-kilometer long accelerator, and it actually crosses the Swiss-French border 4 times, I think. It goes in and out of France twice, so it crosses the border 4 times. So somebody was asking on TikTok, can I name the next discovery particle phase? If you are the theorist that comes up with the theory for the new particle, and you can call it whatever you like, the difficulty is getting other people to call it that too. So Max Power says, suspend a drop of water in the collision chamber and fire the particle into it. So that's actually, yeah, that's quite interesting, because I don't think the particles within the drop of water would be as dense as the other proton beam. But we do, thank you so much. So welcome to all the people who are joining. We're going to keep going until about 6 p.m. my time, so we've got loads of time to have a look around and ask questions. About the water in the detector. So we don't use water, mainly also because we have a lot of electrical equipment, but we do fixed target experiments as well. So what that means is, instead of at the Large Hadron Collider where you're colliding 2 beams of protons in opposite directions together, a fixed target is where you fire 1 beam at something that's fixed, and it's just a different setup for a different experiment, and allows you to explore different properties of matter. So there was a question on YouTube that I was looking at. So Andreas was asking, what trajectories do the particles and please tell me if I say your name wrong, it's Andres, right? What trajectories do the particles follow in these regions of the magnets? So it depends on the charge of the particle and on their momentum, but they go from the center. So let's go back to this, because we're going to go this way anyway. So they go, if there was no magnet on, they would start at the center. Sorry, YouTube can't see. They would start at the center and they would go out in a straight line. So like this line here, it would just be a straight line. But because it's curved, you would get like a curve like that. And that helps us to understand what types of particles. I've been watching for 20 plus years. I just made a particle joke and got a response. Life is complete. I'm glad that I could help. So there's an arrow on my screen on YouTube and I don't understand it. So we're going to go this way, and I'm going to take you to go and see the detector from a different view. So what I'm looking at now, I'm not going to walk into the wall, don't worry. This is actually the Large Hadron Collider. So I'm currently parallel with it. So if you can imagine, the beams go sort of in that direction, like that. And they collide in the center of our detector that way. And so right now I'm at the back of the detector, so we can really get very close. I do wonder what happens if excellent, I can press the button. So there's a great question from Aditya. I hope I said that right. How can we, so this is on YouTube, how can we detect the particles who are in the center and their path is collinear to the proton? So I guess what you mean is, and correct me if I've misunderstood, if there's a collision in the center of our detector and then the particles carry on traveling down the detector. So in some situations, we unfortunately just can't measure them, and it's just a limit of the fact that we have surrounded as much of the detector as possible, but there are some gaps very sort of close to the beam line. But what we do have, and what's a really interesting addition to the experiment itself, and it's not shown in this diagram, is that 200 meters, so that's the collision point here, 200 meters down the beam pipe of the LHC on both sides, we have what we call forward detectors. So forward is confusingly in both directions, but what that means is it's close to the LHC. And the reason that we have these forward detectors is that sometimes the protons don't actually collide in the detectors. They might, because they're very closely packed together and they're passing by each other. What might happen is they might just go past each other and exchange a particle between them. So they could exchange some photons or some other particles between them, and that would cause a collision. Well, it would cause an interaction, sorry. So it would cause something to be formed in the center of that interaction, but the protons themselves will continue. So they continue down the beam pipe. But if anyone has ever done a spectrometer measurement, a mass spectrometer measurement, then they may have observed in their experiment that something with a slightly different mass to everything else will not travel in the same path down your experiment. And so essentially what happens is the protons share an interaction in the center of here, but they don't break up. And then they carry on down the beam pipe, and we measure them in our forward detectors. And this allows us to then go back and look at what happened in the center. And it's a much cleaner environment because we don't have a lot of the other messy particles that happen during those collisions. So that's quite a complicated description, but what I'm trying to say is it's a great question asking about what happens close to the beam pipe, and it's something we've added onto our detector, and we're studying to try to understand these different processes too. So we put as much information in our detector as possible. So let me turn this around and say, there we go. So you can see me as I'm walking around. So I'm, yeah, just gonna go down these stairs. And then we're gonna go and look at the detector from another angle. So here you can see behind me, so that's the LHC. So now we're kind of underneath it, that's the support structure for the LHC. And we have to keep it very cold because the magnets that are used in the Large Hadron Collider are superconducting, like our toroid magnets and our solenoid magnets. And that means that the cables that are used for that magnet have zero resistance, but they have to be very cold because we don't have the technology yet to do superconducting magnets at room temperature. So we have to use somebody. So Dave on TikTok says that they use a spectrometer at work. Excellent. So was the tetraquark detected in the LHC? So that's a great question. So yes, it was. Sadly, not by Atlas. It was by one of our sibling experiments called LHCb. And so tetraquark. So let me just explain that. Let's tilt this down a little bit. You can see as well. So I'm just going to stand. You get to see the detector too. Oh no, we don't like that. Let's do it this way. Unfortunately, they didn't install lots of fantastic lighting for me in the cabin to be able to share for these visits. So I was talking about the tetraquarks. So yeah, that's a fantastic question. And to explain what a tetraquark is, in a proton, so a proton is what we call a composite particle. It means it has other particles inside of it, specifically quarks and gluons. Thank you for the nice comments in TikTok. So a proton has 3 quarks inside of it. We also have other types of particles that have 2 quarks inside of it. And when I started my PhD, that is pretty much all we knew that existed. Let me take these headphones off. There had been searches for particles with more, but we hadn't observed them. And recently, very recently, LHCb, and then I think also Bell 2 was it in Japan, measured these particles with 4 quarks inside. So that's what a tetraquark is. So we call it an exotic type of particle because it's not really seen every day. but it can be created from collisions in the Large Hadron Collider, and then we can study it. And then also LHCb discovered a pentaquark, which is 5 quarks inside a composite particle. And what they're still trying to fully understand is whether or not these tetraquarks and pentaquarks, are they really 5 quarks all combined together equally, or is it a sort of almost a molecule where you have a 3 and a 2? So understanding the substructure of tetraquarks and pentaquarks is really interesting to better understand how they interact together. So I'm going to just show you the new small wheel down here. So I'm going to turn the cameras around again, and then there's a great question. I mean, I'm sure there's loads of fantastic questions that I've been missing, so I'm very sorry. If I do miss your question, please put it again in the chat, and I will try to get to it. So let's turn this around again, so you can see. So I've come down the stairs from this way, along here, and now it's time to see the new small wheel. So this is the upgraded segment of the small wheel that was installed in the cavern. So what I'm going to carefully try to do without breaking my setup is show you up. There we go. So this is the shaft. So up there where you can see at the top of those pipes is above ground. So that's where I started just before this tour. And then I came all the way down. So as I said before, I'm 100 meters underground. Well, technically that's 100 meters underground on the ground. So I guess now I'm about maybe 20 meters up. So this is the new small wheel. So both of them have now been completed and installed in the cavern, which is a fantastic achievement. It took many, many years, and so many people, hundreds of people, to design, to construct these better detectors. And so what they do is they will give us more precise measurements and quicker measurements of these muon particles, which will really help in our data collection when the LHC starts up again next year. So there's some questions about why are we underground. So there's a couple reasons why we are underground. First of all, there is radiation that comes from the detector and from the accelerator if you were right next to it when it was running. And that would be too dangerous for people to be near the detectors. Let me turn this around and then see both at once. Oh no, we don't want to end. There we go. So hopefully you can still see the muon wheel behind me. So yeah, so it is radioactive, and somebody's asking why is it radioactive. So the particles that come from the center of the collisions, so these protons collide, and then they create spin particles. This is radioactivity. It's highly energetic particles passing through matter. So you have alpha radiation, which is basically a helium without its electrons. Beta radiation is highly energetic, electrons or positrons. Yeah, so there's also a comment in the chat on TikTok that it helps hide it from background radiation, background particles. So yeah, why is the detector underground? So the first thing is it's for safety, to make sure there's nobody near the detector when it's running, and that's because it is not. You don't want to be next to it due to the radiation. It protects it from the particles that come from space, so it protects the detector from the particles that come from cosmic rays, which are raining down on it. It doesn't stop them completely, and actually we do use these particles, these muons, to calibrate our detector. So what that means is there are muons that come from the sun, and well, there are particles that come because of the sun and other particles in space, and they hit our atmosphere, and they travel down, and then they pass through our detector, so in a straight line. And while we're not running, while the LHC isn't running, we can use these muons from cosmic rays to check that our detector is in the right place. So we can turn it on, we can wait because it takes a long time to collect enough of them, and then we can see where all the different signals are coming from, and that helps us to align our detector. So yeah, 2 reasons that the detector is underground is to protect people and to protect the detector itself from cosmic rays. And then another one is also just cost. So the LHC is 27 kilometers long. And so to have that much real estate essentially in Switzerland is too expensive. We couldn't possibly do it. So let me just check that I haven't been missing. So there's more questions. So one of them from YouTube is, when the particles interact with the detector's surface, do they lose energy? So yeah, they do. And sometimes that's intentional. So for the calorimeters, we want them to lose energy because that's how we measure how much energy they have. But especially for the center of the detector, so for the tracking detector, we don't want them to lose any of their momentum before they get to the calorimeters, because that will degrade, it will ruin our measurements. And so we try to put as little material as possible in their way. So thank you so much for joining. If you have just joined recently, and just to let you know that I am, we're currently looking at the Atlas detector at CERN. So this is one of the 4 main detectors in the Large Hadron Collider. So we have a fantastic question on YouTube, which is, apart from protons, what other particles are collided inside? And so yeah, it's not only protons that get collided. So we also collide heavy ions, and by this I mean you take an atom, a heavy atom, so like a lead is one of the ones we collide, as well as oxygen, and we take the electrons away so that it has a positive charge, and then we either collide those together or we collide the heavy ions with protons. And often this is done, or the main reason that we do this kind of collisions is because these heavy particles, when they collide together, they recreate the conditions from the early universe. So just fractions of a second after the Big Bang, and we call it the quark gluon soup. It's not very tasty, but you can think this kind of soupy mess of high energy and particles. And so these heavy ions, because they're more massive, we can collide them together and recreate these conditions. So this is why, if you ever hear anyone saying that we're trying to create Big Bangs in our detectors, like CERN is trying to create a Big Bang and create the universes, that's not true. But what they've got that from is that we're trying to recreate the conditions in a controlled way in a small, very small space in the early universe. But this quickly dissipates. These particles will change into lighter particles, and then they go away. Will that soup help with your diet? I mean, it's not a healthy soup. I don't don't recommend eating it. So yeah, we've had a look at the new small wheel here. So we've got a question: would it be helpful to have a collider in space? And we did have a good question earlier. Actually, just before I answer that, I'm going to show you here. So this is the LHC. Here, so you should be able to see that there. So that section right in the center is the Large Hadron Collider, and so you can see that it goes across like that and collides in the center of our detector over here. So where should we go now? I think I might go up. Oh, there's a great view of the detector from up there. So I'm going to go get some steps in and answer some more questions. So yeah, the question was, let me turn this around so we can see each other. Well, let's say that. I don't get to see you. The question was, could we have a collider in space? And there was also a question earlier that I saw that was great, which was, will the next collider be bigger or smaller? These are both great questions, and I'm going to kind of answer them both at the same time. So the reason that we're colliding these high energetic particles, as I was saying, is to try to recreate the conditions in the early universe and to create particles that exist in our universe. The Higgs boson has always existed in our universe. It's just that we didn't measure it before because it doesn't hang around for very long in that form. So we had to provide enough energy to get the universe, quantum mechanics, to create some Higgs bosons for us that we could measure, and then that confirmed our theory about how mass is given to particles. Whew. Talking and working at the same time. So, as we continue to try to understand the structure of the universe, oh, thank you so much. So there's a really nice comment on TikTok saying how much they like his TikTok account. So I'm really happy to hear that, and I appreciate it a lot. Thank you. So you can't watch this tour back later on TikTok, but I might be able to make the YouTube video public. Either way, I get to keep a copy of these, so maybe I'll find a way to put them somewhere if people want to watch them. The thing is, the thing about the live tours is I find them a bit more informal, like hanging out, asking questions, and I think watching back you don't necessarily get the same atmosphere, but not everyone can make it, and so it's also nice so that people can watch it later. What can we see from here? No, I'm going to keep going up. So what was I saying? Yeah, with the Higgs boson. So we have a fixed energy of our collider, and this is linked to essentially the magnets that we have in the Large Hadron Collider. So I made a video quite recently explaining that the maximum energy we can have for a hadron collider, and protons are hadrons, these are particles with, ooh, gonna lose my headphones. A proton is a hadron, so we have the Large Hadron Collider, and the limit for these heavier particles is the magnet strength that we have. And so I can't think, walk and talk at the same time. The limit is the magnet strength. So if we want to go to higher energy, if we wanted to see if there are particles that are more massive that we require higher energy for, then we either need to build a bigger accelerator or we need to have stronger magnets. We are working on ideas for both. So there are many people working very hard to try and design stronger magnets that mean we could stay at the same radius of the collider and just have stronger magnets to bend. Oh, I'm just going to keep going. Where am I going? I think I went too high, too far. I want to show you the detector from up here. Oh, I've gone too high. All those stairs were not worth it. Anyway, thank you so much for joining. So it is on YouTube, and hopefully I will be able to make it viewable on there. So there's a question here on TikTok saying, did I get lost in here in the beginning? Yes. Oh, who says I'm a twin of someone? I can't find the comment. Who am I a twin of? Okay, so to get to the question that I was originally trying to answer, and I was getting distracted by trying to find the path. If we want to build bigger accelerators, eventually we're not going to have space on Earth to do it. So there may come a point where it might be more cost effective or just safer and better to put them out in space. So there are, a lot of proposals around of what kind of size accelerator we would need. Welcome, nice to join. Oh, thank you for the candy canes. I didn't see the animation. Oh, but that is very on theme with Christmas. So I'm here now, so I can now actually think properly. So we might want to put them in space, especially if we want to go to what we call the Planck scale. So the Planck scale is this ultimate, these are the ultimate scales of the universe. And it could be where the final physics that we want to understand is located. And so then we would really have to go to incredibly massive particle accelerators. And I did do a calculation once to work out what size of accelerator we would need to get to the Planck scale. And it's something like, this is not a direct quote, but it's something like a fifth of the way from here to the sun. And we would have to have the ultimate magnets in that accelerator, which is at 1 billion TeV. That is the highest strength magnet you could ever create, because after that, when you put in more energy, the magnets just, they absorb the energy and create new particles rather than creating a stronger magnetic field. Okay, so the reason that I talked and got out of breath and distracted all that way is because I wanted to show you the detector from up here. So let's tilt YouTube down so it can see it. So I just really like this view of the detector. I'm going to hold both phones because I feel like we get it all in at once, which is very nice. Oh, welcome. Great, so I've missed so many questions, I'm sorry. So, great question on YouTube. There's so many, I mean, all these questions are great. Everybody, first of all, if you any question you ask is fantastic, because it means that you're engaged and thinking about what's being said, so I love it. So there's a question on YouTube, let me find it again. Wouldn't the cosmic rays be a major problem with Space Hadron Colliders? Absolutely. That is one of the biggest problems. So on Earth, we have our atmosphere and our magnetic, so it's not really the atmosphere that does it. We have our magnetic field that surrounds the Earth, and it deflects a lot of these cosmic particles away from the Earth. And this is why we get beautiful northern lights and southern lights. These auroras that surround the Earth are the deflection of these charged particles by this magnetic field. When you go, and this is why the International Space Station is at the height that it is from the surface of the Earth, because it's still basically within this shield. So the astronauts, when they're on the International Space Station for 6 months, they do get a higher amount of radiation than they would get on the ground, but they're still mostly protected. If you then want to go into, if you want to travel to Mars, or even just spending 3 weeks on the moon, you no longer have this protection from the Earth. And so it's something that long-term space missions really have to think about. How do you protect your hardware, your electronics from radiation damage? And then also, how do you protect your people, which is very important. If you want to send people on a, say, a 3-year mission to Mars and back, how do you make sure they come back still as healthy as possible? And so the same problem would happen for our accelerators, and specifically for our detectors, if we put them in space. As soon as you get away from the protection of the Earth's magnetic field, then you would have this problem. So you would not only damage your detector from the high energy particles that were coming from your collisions and measuring them, you would also have to contend with all of the particles that are out in space whizzing around, damaging everything. So it's a fantastic question, and something that really has to be thought about in many different fields, and something that it's a connection between the work that we're doing at CERN and sort of space exploration. We can take what we learn, and actually one of the reasons I'm so excited about this is I did my PhD on working to make the detectors right in the center of our detector, which is over here, more radiation hard, more able to withstand the radiation damage that they get when they're in use. And so then this is something that we can learn from each other in the different fields and make sure that all of our scientific endeavors are protected from radiation damage, and particle damage is a big problem. So I'm sure I've missed lots and lots of comments. If I didn't get to your question, please put it in the chat again, and I will try to get to it. And thank you so much for joining. I hope you're enjoying the views. So if you have just joined, Actually, let me just try and hold you steady. I'm going to put my headphones in my bag because I keep dropping them. And then my running headphones. So I'd be very sad if I lost those. Sorry for this intermission. So we've got about 20 minutes left of the live. And it won't be the last live, probably even of the year. I'll answer more questions from home, but we will shut CERN down for the winter even more than it already is. So we're not running the LHC right now, but people are still here working on all of the hardware. And doing data analysis and stuff like that. But we do close the site for Christmas just so that everybody gets a proper break. So it's not, at the moment it's not just shut down for winter, so there's a question, why is it shut down for winter? Right now we've been shut down for 3 years, and this is because we have been upgrading and repairing both the accelerator and the detectors. So for example, I've been talking about this detector here. So this is the new small wheel that you can see next to that magnet system. And this was one of the huge Atlas upgrades that we did over the last few years. So people worked very, very hard. My colleagues were working incredibly hard to get this constructed and then lowered into the cavern and installed, ready for data taking next year. But when we do start running, so we're going to start running again hopefully in May. Well, the Large Hadron Collider should start running before that, and then we're hoping for high energy collisions again in May. And then the reason that we shut down for the winter is because we do use a lot of electricity. This isn't, we're working on better ways to improve our electricity usage, but over the winter we get all of our electricity from France, and French homes need heating over the winter, so we make sure that we're not taking more than we need, and so we stop running. So, and somebody on TikTok's making a joke about the weather. People make comments about CERN controlling the weather, and my response to that is, especially if you were here today, come and visit Geneva in November or December. The weather is awful. If we had any control over this, it would be glorious sunshine, and it would be snowing, because a lot of people here like to ski, but it would not be grey and cloudy and just miserable, basically. So there's a comment, can't use up the entire country's electricity. Yeah, we do, we manage our timetable so that we're responsible with the electricity use. What do you fear of missing out when it comes to CERN discoveries in your field of science? I really want to know what dark matter is. I think this is a huge, huge question. Okay, so thank you for the rose. So Robot said the first thing that went through their mind was that this is a particle accelerator, and then they read the description. So let me answer that. Thank you for the rose. Let me answer that question. So we cannot save all of the data that we collect in these collisions. So the collisions happen in the center of our detector, and there's just too much of it. So we actually have to throw a lot of it away, partly because it's not actually interesting. The same processes are happening again, and we don't need to analyze those again. But we have to design very sophisticated software and hardware to make a decision of what data to keep when we're running. We call this triggering. I talked a little bit about it earlier when I was discussing the Muon system. And we cut it down to about 1 kilohertz of data. And so the biggest thing that I would be afraid of missing is something really interesting in our detector. Something interesting process happens, and we just haven't looked for it. So one of the sort of newer theories and ideas of looking for dark matter and other new physics is that maybe these particles, they get created in the center, but they could travel in our detector a little way before we actually measure them. And so we call these long-lived particles. And this means, that they travel before we measure them. And our data selection software and hardware is not really optimized for that kind of particle. And so people have worked very hard to add this in to our data to be able to look for these kind of events. So I think that would be my biggest concern, is like missing something really interesting because it's so very rare and we didn't think of it. So thank you for the comments. But the ways that we control for this, let's give this a try. I just want to show you a different view as I'm talking. One of the ways that we control for this is that first of all we just keep a little bit of data. So over there you can see Zilka. Sometimes we just keep random selections of the data, which is good to look back later and see if we forgot anything. And then sometimes also on top of that, we are designing new trigger data selection tools to add into our next set of data. Excellent. So there's a podcast, Omega Tau has a really great episode where they go in depth of how various levels of trigger done. Great. Yeah, I mean, these things are it's very, very, I want to say complicated, but I don't mean that in a way that it's not possible to understand it. It's just very sophisticated, and there are a lot of people working very hard in order to ensure that we keep all of the interesting data that we can. And we do have to make decisions because we just don't have the ability to keep all of the data, and we don't have the storage for it. It's terabytes and petabytes of data, and we just couldn't possibly keep it all. So yeah, there's a question here in TikTok saying, is this the Hadron Collider? It is. Sorry, my voice is going to go from talking for a whole hour. This is specifically the ATLAS detector on the Large Hadron Collider at CERN. So we are, I guess now I'm about 70 meters underground because we're quite near the top of it. But here you can see the detector. So let's see, I'm going to keep going up a bit more. You get another view, and then I'm going to go back down and see it from another angle. So I do love being able to see the new small wheels in. It's such a great achievement that these were installed. Thank you so much for the rose. So there's a question in TikTok, is it possible to create a black hole in the LHC? Just some people. I just want to make sure that keeping out of each other's way. So the question, can you create a black hole at CERN? No, basically, is the short answer. Especially not the kind that you think about when you think of astrophysics and the ones in space. These huge black holes that are guzzling matter and sucking in anything around them. There was a proposal, a theory, a suggestion, like a hypothesis that micro black holes could be created in highly energetic particle collisions. But if so, they would have already been happening, they already would have been created in our atmosphere. So we already knew that micro black holes were not being created. Sorry, there's lots of people now below me, and I was just wondering which direction they were going to. So we already knew that nothing dangerous would happen with these collisions because the particles I was talking about coming from outer space hit our atmosphere. They create higher energetic collisions than we get in the Large Hadron Collider, and nothing has happened over the last few billion years. But there are people analyzing the data to see if there's any evidence of any potential micro black holes, and there are not. And even if they were created, they would fizzle out rather than grow in size. 'Cause So I'm just waving to the colleagues. So I don't know if they wanted to come this way, but I guess not. Okay, sorry, I was distracted by all the people. Yeah, so there's a comment in the TikTok saying you didn't know that there was a basis for the black hole conspiracy. Yeah, it did come from, you know, some really sensible suggestions of the kind of physics that could be happening. But people hear the word black hole and they think of the ones in space, especially like the supermassive ones in the center of our galaxy. And yeah, it could cause some concern with people. But no, that's not happening in our collisions. So thank you for the hand wave. So how many detectors are there at CERN? That's a great question. And also there was a question I saw earlier, I don't know if the person is still here, because there's not just the experiments happening on the Large Hadron Collider. Let me turn this around. Like this, and then we can hang out. So, can you still see? Yeah, great. So there's not just the detectors happening on the Large Hadron Collider. So it's not just ATLAS and CMS and LHCb and ALICE. There's also detectors in our antimatter factory. So there's a question, what is ATLAS? So this is ATLAS. It's the name of this experiment here at CERN. And it's one of 4 main experiments on the Large Hadron Collider. And so we also have other experiments that are looking at studying antimatter in more detail. We have the cloud experiment, which is studying sort of the formation of clouds to do with particles, cosmic rays, different kinds of conditions, which is, I guess, where people think the controlling the weather thing came from. Because we are studying how weather forms, but not controlling it. And it's the same with all of the measurements that we're doing on the Large Hadron Collider. We're not really creating anything in a new way. We are making a controlled environment to understand what is already there. So when people hear about the Higgs boson and they hear that it could be linked to the universe ending, which if you want to know more about that, then Katie Mack has a fantastic book about how the universe is probably going to end. And they think because we're creating Higgs bosons, therefore we're causing that to happen. And that's not true, we're just observing. So we're creating controlled conditions so that we can observe what our universe is like and better understand the very small structures in our universe. So there's a comment here on TikTok about Atlas Open Data in the website is a very small fraction, so I can hear my voices going. Can I hold this like this? Yeah, so on YouTube somebody's saying vacuum decay, exactly. So that's what the link to the Higgs boson end of the universe is. And to explain that very quickly, it could be that the settings that the Higgs boson has are not the ideal settings for it. Basically, like its properties. There's a joke in YouTube about don't shake hands with someone who's made of antimatter, because yeah, that would be very bad. So the Higgs boson's properties might not be the ideal ones for the universe, and everything in physics in the universe likes to be in their lowest energy state, their most ideal state, and so it could be that the Higgs field collapses into its ideal state at some point, and this bubble would just travel throughout the universe, and then it would change the structure of how particles interact with each other, and this would be very bad. The likelihood of it happening is so very tiny that it's almost non-existent. But that's one of the reasons that we are trying to understand these particles better, because that can help us to understand the universe, the fate of the universe on sort of the billions of years scale. But when people hear these kind of stories and link to the Higgs boson, they think by creating them in our collisions, we are encouraging this to happen, and it's absolutely not the case. You'd need significantly higher energy, and if this hasn't already happened in black holes, then I think we are safe. So I've missed a whole bunch of comments and questions again. I really wish, because on TikTok at the end of the live, it saves the video. I can't see with my French. It saves the video for me, but I never get to go back and look at all the comments again. So I always miss loads of interesting comments. Okay, so we've maybe got a little bit of time left, because also I can't stay in the cavern if there's no one else down here. And so there were quite a few people earlier, which is good. But we just have systems to make sure everybody's safe here at CERN, and one of them is that you shouldn't be alone, especially in the cavern. Thank you so much for the compliment about the helmet. I had a different one for a really long time that didn't have a chin strap, although this one needs tightening. And I was always nervous, there we go, safety first. I was always nervous when I would look over the barrier that my helmet would fall off and drop and break something, and then I would get in trouble. Okay. Does something happen automatically if you're the last one? Yeah. If you're the last one there. So on TikTok I have a question. Yeah, if I'm the last one here, I get a phone call that says, from the safety officer, saying, time to go. And so I try not to get the phone call, because also it's not, you know, they want to go home at the end of their shift. But the reason I do these late is that I know that a lot of people are joining from the US and Canada, and the Americas in general, and so I want to also have a socially acceptable time for you. And then maybe I'll try and do some in the morning now that I've got YouTube working, which seems to be great. I hope it's been good for you on YouTube, which means that people who don't have TikTok, and I know that, for example, TikTok is banned in India, then people can watch it on there as well. So I've now come to the other side of the detector. Just have a bit of a walk around. Ooh, I like this view. Hold on, let me turn the camera around. There we go. Let's tilt this down like that. Hopefully it doesn't fall. So if anyone has just... excellent. I heard that it's good timing in Canada. That's good. So if anyone has just joined, welcome. We've only got a little bit of time left before I will have to end the live. But I am here underground for the Atlas experiment at CERN. So this is one of the 4 main experiments. So while I've got people here, let me float a new idea. One of the lives that I was thinking of doing is a lot of my friends are colleagues here at CERN, and we were thinking of having evening chats, which is essentially we would sit in the restaurant here at CERN, set up the phone and chat physics with each other, and answer questions. Do you think that would be something people would be interested in, to hear from more people at once? Oh, thanks for the donut. Oh, you're making me hungry now. Excellent. So it's not really supposed to be like a podcast, because podcasts are much more structured. It would be like you get to hang out with us if you would want to. Obviously you don't have to. Thank you for the rose. So there is a person down there. I don't know if you can see down there. I'm not going to film them too much. There's a person down there working on the Muon wheel. Good, that's great. And also I haven't forgotten, because I have promised a lecture called What is Particle Physics Anyway? That's my working title. And so I have been working on that, and that will happen next year. And by next year I mean next month. And especially now that I've got YouTube. Well, I could stream on YouTube before, but I had to always do it from my computer. Now it seems to be working very nicely from my phone. So yeah, if you're interested in the lecture, that will definitely be on YouTube. I might have TikTok going at the same time, just to show a behind the scenes. Yeah, I have. There's a question on TikTok. Do you just have 2 phones strapped together you're filming with? Yep. So I have a frame with one of the phones, and I have the other one sort of tied on top, so that they're pointing in the same direction. Excellent. It's very noisy on this side. You can probably hear it. It got noisier. What is funny? I missed it. Oh, the comment. Person doing their job, 70 people. Yep. We've also got people on YouTube watching as well. So let's answer a couple. It's too noisy here. I'm going to go back this way. And what I'm going to do is I'm going to start heading out of the cabin so that I can let. See this? And then yeah, I can answer questions on the way. So there was a question in here. Sorry, let me just get my hand. What's the biggest achievement of the Atlas detector? Yeah, there is good reception down here. It's because we have dedicated Wi-Fi, which is super useful. So here you can see the detector. So the biggest achievement of the Atlas experiment, we would have to say, is the discovery of the Higgs boson. So this is a particle that we were looking for, scientists, not me personally, but we were looking for over 50 years. So it was theorized in the 60s by 6 theorists who kind of came up with these ideas, a couple of them in groups, but basically independently. And then we were building bigger and bigger accelerators to try to understand how do the fundamental particles in our universe, how do these, like electrons, top quarks, all of these particles, how do they get mass? Because our theory, we have the standard model of particle physics, doesn't explain it. It explained that all these particles existed, and we discovered them and we confirmed this, but it didn't explain how they got mass. So this is what I'm explaining right now. So someone on TikTok, so is it Jess, says, I still don't understand what the Higgs field is. So specifically, the theory came up with this field, which is essentially something that's throughout our universe that has a specific measurement at different points. And so like an electric field, you have the electric charge at different points. What floor am I on? 4, perfect. So you have the fields throughout the universe, and when a particle interacts with this field, it gains mass. And my favorite analogy, and it's perfect for this time of year, is that imagine that you have a field of snow just everywhere, and the amount that you interact with the snow, how much you get slowed down with it, is how much mass you have. So if you are like a top quark, then you're in really heavy snow boots and you're just trudging along through the snow. You're very massive, and so you're very slow. If you are on skis, you're essentially like a neutrino, barely touching the snow, and so you're interacting with it a bit, but you're just whizzing down, not being stopped at all. And then photons are basically not interacting with the snow at all, and they have no mass. And so I've lost my thread because I got distracted by more questions. So we have this field. It was predicted by the theorists. We were searching for it for many years. And back to the snow analogy, if you have the field interacting with itself like a snowball, a massive snowball, this is the Higgs boson. And to really explain the discovery of the Higgs boson, it's like finding a snowball, and that confirms that somewhere there is a whole field of snow. So if we find, Legolas, exactly, Legolas is essentially a neutrino, and who's the heaviest? I mean, I guess Gimli would be quite a massive particle because he'd just sink in. So finding the Higgs boson confirmed that the Higgs field exists. And that is a huge achievement. It really explains something very significant about the standard model and our universe. So I think that's a perfect note to end on. So I focus mostly today on the detector itself. Let's turn it around and take one more look at this beautiful detector, because we're underground and looking at this detector. So I promise this won't be the... I thought my phone was ringing. This won't be the last time we go underground, but it is the last time underground together in 2021. So thank you so much for joining. I see some people say they have to get back to work. I will do more lives where we can talk more about the specific physics, about all the different types of particles, some of my favorite theories that we're looking for. I'm going to be making more videos, even though things are a bit weird right now. But thank you so much to everyone for joining, both on TikTok and on YouTube. I really appreciate it. Was that another baguette? Yeah, perfect. Thank you. Let me turn this around. So thank you so much for joining. I've really enjoyed talking to you. All of the questions were fantastic. I'll be making some more videos and also scheduling a few more lives. Let's put this down. Favorite particle, very quickly, the top quark. This is the one that I work on. It is the most massive particle that we know of in the standard model, and it really helps us understand a lot about the structure of the universe, interactions with the Higgs boson. We're using it to try and search for dark matter and other new physics. So my favorite is the top quark. So thanks again for joining. I really enjoyed this. I hope you have too. Let me know if you have any questions, and if you're not subscribed already or following already, then please go ahead. That really helps, and then you'll get notified if I do any more of these lives. So thank you, take care, have a great evening, day, morning, wherever you are, and I will chat to you all again soon. And we'll end with a beautiful view of the detector. Thank you for the wave. All right.